This is our electrostatics video number 5, and I'm going to do mostly practice in this question, and maybe there's going to be another video for practice number 6, and the link is going to be for the next one in description as well. Here's number 39. A positron is given an initial velocity of 610 to the 6 meters per second to the right, and the velocity of the speed of light is 310 to the 8 meters per second, just to compare. So a positron is given an initial velocity of 610 to the 6 meters per second to the right. It travels into a uniform electric field directed to the left. As positron enters the field, its electric potential is 0. What will be the electric potential at the point where the positron has the speed of 110 to the 6 meters per second? So in this question we have kinetic energy of the positron is changing. So I'm going to say the change of the kinetic energy, or the kinetic energy that positron is losing, is going to go into the change of its potential energy. And the positron is the electron with a positive charge, so it's called positron. It's the same size as an electron but has a positive charge instead of the negative charge like an electron has. And for the potential energy, I'm gonna use the formula that you see right here on the top, because they mentioned electric potential is 0. So at first it starts with the potential energy of 0, and then the potential energy is increasing. So I'm gonna use that the work is equal to the change of the voltage times the charge, and the charge is positive, but the same charge, the magnitude of an electron. So, and this is going to be our change of the potential energy. So the work done to slow it down of the positron is taking away the kinetic energy but gives the potential energy. So the kinetic energy is equal to the final 1/2 its mass of the electron, velocity final squared minus 1/2 its mass and velocity initial squared, and they give you initial velocity and they give you the final velocity. So here's the final velocity, so final, and that is equal to Q delta V. So if I times them all by 2, I have, and I'm going to take the mass out from the first, from the left side. So the mass is out, and I have the V final squared minus V initial squared, and times both sides by 2 gives me 2Q delta V. If I divide both sides by 2Q, so if I divide both sides by 2Q, then I'm going to have 2Q on the other side. And the charge of the electron is negative 1.6, 10 to the negative 19 coulombs. And because it's positron, it's just the positive part. And the mass of the electron is 911, 10 to the negative 31st kilogram. And you usually given these numbers on AP exam, so you don't have to be memorizing anything. So now if I plug in my numbers, I will find that the change of voltage, or the change of the potential and the potential difference, is equal to, so I got 99.6 volt, and I did not keep the negative sign here, even though it appears when you subtract. I did not keep the negative sign because the electric field line is going from the positive to the negative. If it starts from 0 as it enters, so here you have 0 volt, then as it goes closer to the positive charge, because the electric field line go from the positive to the negative, it gets to the higher potential, and higher potential cannot be negative, so it's going to be 99.6 volt positive. the negative appears only because you find how much kinetic energy is lost, but that's the potential energy gained. Let's look together at number 41. And in this problem, they say in the diagram shown on your right, point A and point B are separated by the distance of 30 centimeters. How much work must be done by an external force to move a proton from point A to point B? So the voltage is equal to the work done on the charge, and so if I'm looking for the work is going to be, in this case, change of the potential energy times the charge. So if I'm calculating the work, it is a proton, so the charge is 1.6 10 to the negative 19, and times the change of the voltage. So this equal potential line is 50 volts, and this equal potential line is 60 volts. So the change, it went from A to B, so it gained 10 volts. So the change is 10. So that gives me 16 10 to the negative 19 joules. In problem 42, they say the figure below shows an isolines of constant electric potential. Which way does the electric field vector point at point A? So here is our point A, and because it's a positive charge, electric field lines are going to be pointing away. So that would be the answer for A. If we place an electron at point A, in which direction will it receive a force? So if there is an electron at point A, then the force acting on it is going to be toward the positive charge, but there are two positive charges. So one is going to be toward this positive charge force, and one is going to be toward this positive charge. So there will be resultant force. So this one's probably shorter. So there will be resultant force. We have to do parallelogram, and there would be the resultant force acting on this electron. For C, they say, does the electron gain or lose energy when it moves away from point A to point B? The point B is on the 50 volt equipotential line, and the point A is on 100 volt equipotential line. So the work done to move the electron from A to B is equal to the charge of the electron and change of the potential difference. So the work is going to be equal to 1.6 10 to the negative 19, and the final minus initial, so I have 50 minus 100, and that will give me 80 10 to the negative 19 joules, and I'm gonna write it negative right here. And let's talk about whether it gains or not. Because it is an electron does not want to move away from the positive charge. Electron wants to move toward the positive charge. So if we move it in higher potential away from the positive charge, it gains potential energy, because the farther you move it away, the more potential energy it has. It's the same as raising an electron above the earth, and then it would be falling down. So the higher you get your electron away, then the more potential energy it has. Then when you release that electron, it will speed up toward the earth. In this case, it will speed up toward the positive charge. So when you rise the electron away from the positive charge, it gains potential energy, and then as it reaches the positive charge after you release it, it loses potential energy and gains kinetic energy. Also, I want to show you something interesting here that we will be doing at the end of AB Physics 2. In this problem, actually let's look at the formula itself. If I wanted to find the work, I could write the charge. Instead of writing the charge, I'm going to say it's an electron, and the change of the potential difference is negative 50. So I could say it is negative 50 electron volts. So instead of saying, because this is measured in volts and this is the electron, so when I multiply them, I can say it is negative 50 electron volts. But then you have to think about whether it gains or loses potential energy, not looking at the sign itself, just from the problem. Because it's an electron, it wants to speed up toward the positive charge. The farther away you move the electron, the more potential energy it has, and the closer it gets back to the positive charge, the more kinetic energy it will gain, because that potential energy is going to turn to the kinetic energy when it speeds up toward the positive charge. Here's a somewhat tricky question, number 46. When a positive 3 coulomb of charge moves from point A to point B in an electric field, the potential energy is decreased by 27 joules. It can be concluded that point B is 9 volt lower in potential than point A, or maybe 9 volt higher in potential than point A, or 81 volt higher in potential than point A, or 81 volt lower in potential than point A. So I'm gonna say here's the charge, and let's call it Q. And then you have equal potential lines. And I'm gonna take and say this is point A, and it's a positive charge. So when it moves from point A to point B in electric field, the potential energy is decreased. So if the charge is positive and you take another positive charge next to A, so here from A, and it's going to move to point B, because for the positive charge, the potential differences between the equal potential lines decrease farther away from the charge. Maybe this is 100, maybe this is 80, and maybe this one is 60 volts. And because the charge that they give you is positive 3 coulombs, when you move it away from A to B, your positive charge does not want to stay close to the positive charge. So when you move it away, it loses potential energy. So here we say it loses potential energy. And if it loses potential energy, then well, they actually tell you the 9 volt difference. So I'm going to take this voltage away so we don't have to look at this. And I just wanted to tell you that it goes from the higher potential to the lower potential from the positive charge. And I have the charge is given and the energy is given. So the work is equal to change of the potential energy of the charge and equals to change of the voltage times the charge. So if I'm looking by how much voltage it changes, so the voltage is equal to the potential energy, which is 27, divided by the charge, which is 3. So that gives me 9 volt. And because I know when the positive charge goes from point A to point B, the voltage is lower the farther away it goes, then the answer is A. So when the charge goes 3 coulomb charge goes from point A to point B, it loses potential and energy of 27, and the difference between the equipotential line where A was to B is 9 volt, the one that we just calculated. In other words, equipotential line A is 9 volt higher than equipotential line B. So I mentioned earlier that 1 electron volt can be rewritten as electron times the voltage. So the work or the energy is equal to the charge times the change of the voltage. So if you plug in the voltage and you plug in, and it's all about the electron, so instead of plugging in an electron, you can write an electron, and if the change of the potential difference was 1 volt, then you would have 1 volt, or you get 1 electron volt. So sometimes instead of writing the answer in joules, you could write it in joules, then it would be 1.6 10 to the negative 19, and if it's 1 volt difference, so the potential difference is 1 volt, you would have times 1, and will give you the answer in joules. So in other words, 1 electron volt, it's 1 electron times 1 volt, is the same as 1.6 10 to the negative 19 joules. So at the end of the course, we will see a few of such conversions or written energy in electron volts instead of writing them in joules. On AP exam, sometimes they have questions related, so within one question they can have different concept tested, and one of them can be this type of question. So this probably would be maybe one of the sub levels of the question, so maybe it's a C or D or something within the question. So here they say a small charge of 3.2 10 to the negative 19 coulombs is moved between two parallel plates from a position with an electric potential of 2 10 to the third volt to another position with an electric potential of 4 10 to the third volt. Determine the change between the two positions. Well, because the new one is 4 kilovolt and the old one is 2 kilovolt, then the change of the voltage between those two is 2 kilovolt, or 2 10 to the third volts. And then the energy gained by moving the charge in joules. So if I want to calculate the energy or the work, that is equal to the charge times the change of the potential difference, and the charge is 3.2 10 to the negative 19, and the voltage is 2 10 to the third. So the answer is going to be 6.4 10 to the negative 16 joules. So that would be in joules answer. And the next one they ask you, so that would be this answer. And the next one they ask you in electron volts. So if I wanted to calculate the energy in electron volts, 3.2 10 to the negative 19 is the same as 2 electrons, because an electron is has a charge of 1.6 10 to the negative 19. So that's 2 electrons, and then I times it by 2 kilovolts, which is 10 to the third. So my answer is going to be 4 kilo electron volts, or 4 10 to the third electron volts. Here's an interesting question, and it is interesting only because you have to derive the formula that they don't give you. So let's read the question. A cathode ray tube, CRT, they used to use this tube in old monitors, if you remember, or if you have seen old monitors that they have, they're not flat, they have the tube inside of them, so they're bulky in computers, monitors, or in old TVs. So a cathode ray tube computer monitor accelerates electrons between charged parallel plates, and that's how the tubes or the old TVs used to work. These electrons are then directed toward a screen to create an image. If the plates are, and they show you the numbers, 1.2, so it's 1.2, so there is a point right there. 1.2 10 to the negative 2 meters apart and have a potential difference of 2.5, so there's 2.5 10 to the 4th volt between them. Determine the magnitude of the electric field between the plates. So I derived this formula in the past in different video, but I'm gonna go over it again. So if you're looking for the change of the potential difference, that is equal to the work done on the charge. So the voltage is equal to how much work you do to move the charge. So the work is the same as the force times the distance over the charge, and the force over the charge is electric field times the distance. So here I have to determine the magnitude of the electric field. So from here I can solve for the electric field, and it equals to change of the potential difference divided by the distance. So the change of the potential difference is 2.5 10 to the 4th, and the distance is 1.2 10 to the negative 2. So the electric field is equal to 2.1 10 to the 6 newtons per coulomb. So what they did in the past, they had these two plates, and electron would accelerate from one plate to another, and then they would have additional plates to cause the magnetic field. So this is electric field to accelerate electron forward. So by the time an electron reaches the screen, it bombards the screen and eliminates the different colors. But they can also use magnetic field, and then they can direct the electron in different directions, and then it will go exactly where you want it and the color will come up. So that's how the old TV used to work, or old computer monitors. Just because I want to review this formula again with you. So what is the electric field intensity? 0.3 meters away from a small sphere that has a charge of 1.6 10 to the negative 8 coulombs. So you know the formula for the electric field is equal to E is equal to the force acting on the charge, and this is the test charge, but there could be a source charge, and the electric field force between the charges is equal to K, and then it's going to be Q of the source, Q of the test, and the distance between them squared divided by Q of the test. So Q of the test and Q of the test cancels, and what I have is Q of the source over the distance squared. And because we're talking about the point small sphere that has a charge, let me see, what is the electric field density? So they don't tell you the point, but it is 0.3 meters away from the sphere that has this charge. So this charge is the source, and this is how far we are testing, how far away from the sphere the electric field is, how strong it is. So I can calculate it as K, which is 9 10 to the 9 coulombs constant, and the charge is 1.6 10 to the negative 8, and the distance is 0.3 squared. So I will get 9 10 to the 9th, 1.6 10 to the negative 8, and here I have 9 10 to the negative 2. So 9 and 9 can be cancelled, so the electric field is going to be equal to 1.6. A 9 and the negative 8 will give me 1, and negative 2 will go to the top and become a positive, so that gives me 10 to the 3rd, and measured in newtons per coulomb. So it's 1.6 kilonewtons per coulomb. In this question number 76, they ask you to determine the magnitude and the direction of the net electric field at point P shown in the diagram. So the electric field from the positive charge is going to be in this direction, and the electric field from the negative charge is going to be toward the negative. So I have this electric field, and I have this electric field, and I'm going to calculate the resultant. So at first I'm going to find this electric field. So it's the electric field of the source, so the formula is K, the charge of the source, and the distance squared. K is 10 to the 9th. The charge is 50 micro, so that means 10 to the negative 6. And the distance is 0.45 squared. So that will give me 2.22, 10 to the 6. And this is newtons per coulomb. And if I calculate the next one, I have the same K, which is 10 to the 9th. The charge of the negative charge, it's 10 micro, 10 to the negative 6. And the distance is 0.15 squared. So that will give me 4 times 10 to the 6 newtons per coulomb. And because they're in opposite direction, the resultant, so the blue one is actually stronger because it's closer to the charge, so this one is stronger. So the resultant is going to be the difference between of them, and that one is equal to 1.78 10 to the 6 newtons per coulomb, and it is directed to the left. So this would be the resultant, directed to the left. Because the stronger one is the one from the negative charge, and if I subtract them, the resultant is going to be to the left, and the value or the magnitude of it is 1.78 10 to the 6 newtons per coulomb. I think we're going to finish our electrostatics video 5, the practice questions, at this point, and the links for electrostatics video 6 is in the description. And thank you for watching, and I'll see you in the next video.